14.2 Extracting the data. When extracting multiple data sources, it is important to note the time intervals of the data. The Yellow Cab data is available at 15-minute intervals, and the City Bike data interval is configurable. To make it easy, let's also request City Bike data at 15-minute intervals. This allows you to make 2 requests at the same interval, in the same DAG, and process all data in parallel. If we choose a different interval, we have to align the processing of both datasets differently. Section 14.2.1 Downloading City Bike data. With Airflow, we have the simple HTTP operator to make HTTP calls. However, this quickly turns out to not suit our use case. The simple HTTP operator simply makes an HTTP request, but provides no functionality for storing the response anywhere. In such a situation, you are quickly forced to implement your own functionality and call it with a Python operator. Footnote 2. By setting xcom_push equals true, you can store the output in XCOM. Let's see how to query the City Bike API and store the output on the min.io object storage. We have no Airflow operator to use for this specific HTTP to S3 operation, but we can apply Airflow hooks and connections. First, we must connect to the City Bike API using the Python requests library and min.io storage using the S3 hook. Since both require credentials to authenticate, we will store these in Airflow to be loaded at runtime. By default, the S3 hook communicates with AWS S3 here. Since we're running min.io on a different address, we must provide this address in the connection details. Unfortunately, this isn't a straightforward task, and sometimes such oddities result in having to read a hook's implementation to understand its inner workings. In the case of the S3 hook, the host name can be provided via a key host in the extras, figure 14.4. Now that we have the connection set up, let's transfer some data. If all succeeds, we can log in on the min.io interface here and view the first downloaded file, figure 14.5. If you were to perform this HTTP to S3 operation more often with different parameters, you'd probably want to write an operator for this task to avoid code duplication. Section 14.2.2 Downloading Yellow Cab data. We also want to download taxi data on the min.io object storage. This is also an HTTP to S3 operation, but it has a few different characteristics. The file share serves files, whereas we had to create new files on min.io for the City Bike data. These are CSV files, while the City Bike API returns data in JSON format. We don't know the file names up front. We have to list the index to receive a file list. When you encounter such specific features, it usually results in having to implement your own behavior instead of applying an Airflow built-in operator. Some Airflow operators are highly configurable, and some are not. But for such specific features, you mostly have to resort to implementing your own functionality. With that said, let's see a possible implementation. This code will download data from the file server and upload it to min.io, but there is a problem. Can you spot it? S3_hook.load_string is not an idempotent operation. It does not override files and will only upload one, or string in this case, if it doesn't exist yet. If a file with the same name already exists, it fails. To avoid failing on existing objects, we could apply Python's EAFP idiom, try first and catch exceptions, instead of checking every possible condition, to simply skip when encountering a value error. Adding this check for existing files won't make our pipeline fail anymore. We now have 2 download tasks, which both download data on the min.io storage, figure 14.6. Data for both the City Bike API and Yellow Cab file share are downloaded on the min.io storage, figure 14.7. Section 14.3, Applying Similar Transformations to Data. After we've downloaded the City Bike and Yellow Cab data, we apply several transformations to map the City Bike station coordinates to Yellow Cab zones and to start accurately comparing them. There are various ways to do this, depending on the size of the data. In a big data scenario, you'd want to apply Apache Spark to process the data using a cluster of machines. A Spark job can be triggered with the Spark submit operator or another operator that could trigger a Spark job, such as the SSH operator. The Spark job would then read from S3, apply transformations to the data, and write back to S3. On a smaller scale, that is, data processable on a single machine, we can apply pandas for this task. But there is no pandas operator at the time of writing, so pandas code is typically executed using the Python operator. Note that Python code is run on the same machine as Airflow, whereas a Spark job is typically executed on other machines dedicated for that task, which will not impact the resources of the Airflow machine. In the latter case, Airflow is only responsible for starting and monitoring the Spark job. If a pandas job is hitting the limits of the machine's resources, it could, in theory, take down the machine and Airflow with it. Another way to avoid claiming the Airflow machine's resources is to offload the job to Kubernetes using the Kubernetes pod operator or a similar containerized system, such as AWS ECS using the ECS operator. Let's assume we apply pandas for processing small data. Instead of demonstrating how to use yet another Python operator, let's look at how we can generalize some components for reusability and code deduplication. We have two datasets stored in /raw. /raw/citybike/ curly bracket ts underscore no dash curly bracket .json /raw/taxi /star.csv. Both datasets will be read using pandas. A few transformations will be applied, and eventually the result will be written to the following: /processed /citybike/ curly bracket ts underscore no dash curly bracket dot parquet /processed /taxi curly bracket ts underscore no dash curly bracket dot parquet. While the input formats differ, the object type into which they are loaded and the output formats do not. The abstraction to which operations are applied in pandas is the pandas data frame, similar to a Spark data frame. There are a few small differences between our transformations, input datasets and output file locations, but the core abstraction is the same, a pandas data frame. Hence, we could implement a single operator for dealing with both transformations. Let's break down how to use this pandas operator. As mentioned, the commonality between various transformations is the pandas data frame. We use this commonality to compose operations on the data frame given three functions: input underscore callable, transform underscore callable optional, output underscore callable. The input underscore callable reads data into a pandas data frame. The transform underscore callable applies transformations to this data frame, and the output underscore callable writes the data frame. As long as the input output of all three functions is a pandas data frame, we can mix and match callables to process the data using this pandas operator. Let's look at an example. The goal of the pandas operator is to provide a single operator that allows mixing and matching various input, transformation, and output functions. As a result, defining an Airflow task glues these functions together by pointing to them and providing their arguments. We start with the input function, which returns a pandas data frame as follows. The transformation function, which adheres to data frame in, data frame out, is as follows. And last, the output function, which takes a pandas data frame, is as follows. Passing pandas data frames between the input, transform, and output functions now provides the option to change the input format of a dataset simply by changing the argument, this to, for example, this. As a result, we don't have to re-implement logic with every change or every new dataset, resulting in no code duplication and more flexibility. Note: whenever you find yourself repeating logic and wanting to develop a single piece of logic to cover multiple cases, think of something your operations have in common, for example, a pandas data frame or a Python file-like object. Section 14.4, Structuring a Data Pipeline. As you read in the previous section, we created the folders raw and processed in a bucket named Data Lake. How did we get to those and why? In terms of efficiency, we could, in principle, write a single Python function that extracts data, transforms it, and writes the results to a database, all while keeping the data in memory and never touching the file system. This would be much faster, so why don't we? First, data is often used by more than one person or data pipeline. In order to distribute and reuse it, it's stored in a location where other people and processes can read the data. But more importantly, we want to make our pipeline reproducible. What does reproducibility imply in terms of a data pipeline? Data is never perfect, and software is always in progress. This means we want to be able to go back to previous DAG runs and rerun a pipeline with the data that was processed. If we're extracting data from a web service such as a REST API, which only returns a result for the state at that given point in time, we cannot go back to the API and ask for the same result from 2 months ago. In that situation, it's best to keep an unedited copy of the result. For privacy reasons, sometimes certain parts of the data are redacted, which is inevitable. But the starting point of a reproducible data pipeline should be to store a copy of the input data, that is, edited as little as possible. This data is typically stored in a raw folder, figure 14.8. From this raw data, you and others can then alter, enrich, refine, transform, and mingle with it as much as you like, which is then written back to a processed folder. Transformations are often compute and time intensive, so we try to avoid rerunning a task and saving the results such that processed results can easily be read again. In practice, many organizations apply more fine-grained separations between the stages of data. For example, raw, pre-processed, enriched, processed, export. No one structure suits all. Your project and the project's requirements will determine how to best structure the movement of data. Section 14.5. Developing idempotent data pipelines. Now that we have data in the raw folder, we will process it and insert the results in a Postgres database. Since this chapter isn't about the best way to process data with Pandas or Spark, we will not discuss the details of this transformation job. Instead, let's reiterate an important aspect of data pipelines in general, namely ensuring a data pipeline can be executed multiple times without having to manually reset state or introduce a change in the results. Idempotency. There are 2 points in this data pipeline where we could introduce idempotency. The first is easy. When transforming the raw data into a processed state and storing it in a /processed folder, we should set a flag to overwrite destination files. This ensures rerunning a task will not fail due to an already existing output path. The second stage, where we write results into the database, is less evident. Rerunning a task writing results to a database might not fail, but could result in duplicate rows that might pollute the results. How can we ensure results are being written to a database in idempotent fashion so that we can rerun pipelines without duplicating results? One way is to add a column to the table that can identify something unique about the job writing to the database. For example, the execution date of the Airflow job. Say we're using Pandas to write a data frame to a database, as shown in the following listing. There is no way to tell when executing df.to_SQL if we're going to insert already existing rows into the table. In this situation, we could alter the database table to add a column for Airflow's execution date. In this example, we start a database transaction because the interaction with the database is twofold. First, we delete any existing rows with a given execution date, and then we insert the new rows. If there are no existing rows with a given execution date, nothing is deleted. The two SQL statements, df.to_SQL executes SQL under the hood, are wrapped in a transaction, which is an atomic operation, meaning either both queries complete successfully or none do. This ensures no remainders are left over in case of failure. Once the data is processed and stored successfully in the database, we can start a web application here, which queries the results in the database. Figure 14.9. The results display which method of transportation is faster between two neighborhoods at a given time. For example, row 1, on Sunday between 8 and 11, traveling from Alphabet City to East Village is, on average, faster by taxi. 330 seconds, 5.5 minutes, by taxi versus 1057.2, 17.62 minutes by city bike. Airflow now triggers jobs downloading, transforming, and storing data in the Postgres database at 15-minute intervals. For a real user-facing application, you probably want a better-looking and more searchable front end, but from the back-end perspective, we now have an automated data pipeline, automatically running at 15-minute intervals and showing whether a taxi or city bike is faster between given neighborhoods at given times, that is visualized in the table in Figure 14.9. Summary. Developing idempotent tasks can be different based on case. Storing intermediate data ensures we can resume partial pipelines. When an operator's functionality does not fulfill, you must reside to calling a function with a Python operator or implement your own operator. Part 4. In the clouds. At this point, you should be well on your way to mastering Airflow, being able to write complex pipelines and knowing how to deploy Airflow in a production-like setting. So far, we've focused on running Airflow on a local system, either natively or using container technologies such as Docker. A common question is how to run and use Airflow in cloud settings, as many modern technological landscapes involve cloud platforms. Part 4 focuses entirely on running Airflow in the clouds, including topics such as designing architectures for Airflow deployments and leveraging the built-in functionality of Airflow to call various cloud services. First, in Chapter 15, we give a short introduction into the different components involved in designing cloud-based Airflow deployments. We'll also briefly discuss Airflow's built-in functionality for interacting with various cloud services and touch on vendor-managed Airflow deployments, which may save you from rolling your own deployment in the cloud. After this introduction, we'll dive into specific Airflow implementations for several cloud platforms: Amazon AWS, Chapter 16, Microsoft Azure, Chapter 17, and Google Cloud Platform, Chapter 18. In each of these chapters, we'll design architectures for deploying Airflow using services from the corresponding platform and discuss built-in Airflow functionality for interacting with platform-specific services. Finally, we'll close each chapter with an example use case. After completing Part 4, you should have a good idea of how to design an Airflow deployment for your cloud of interest. You should also be able to build pipelines that smoothly integrate with cloud services to leverage the scale of the clouds in your workflows. Chapter 15. Airflow in the Clouds. This chapter covers examining the components required to build Airflow cloud deployments, introduction to cloud-specific hooks, operators for integrating with cloud services, vendor-managed services as alternatives to rolling your own deployment. In this chapter, we'll start exploring how to deploy and integrate Airflow in cloud environments. First, we'll revisit the various components of Airflow and how these fit together in cloud deployments. We'll use this breakdown to map each of the components to their cloud-specific counterparts in Amazon AWS, Chapter 16, Microsoft Azure, Chapter 17, and Google Cloud Platform, Chapter 18. Then we'll briefly introduce cloud-specific hooks, operators, which can be used to integrate with specific cloud services. We'll also provide some managed alternatives for deploying Airflow and discuss several criteria you should consider when weighing rolling your own deployment versus using a vendor-managed solution. Section 15.1. Designing Cloud Deployment Strategies. Before we start designing deployment strategies for Airflow in the different clouds, AWS, Azure, and GCP, let's start by reviewing the different components of Airflow. For example, web server, scheduler, workers, and what kind of shared resources these components will need access to. For example, DAGs, log storage, etc. This will help us later when mapping these components to the appropriate cloud services. To keep things simple, we'll start with an Airflow deployment based on the local executor. In this type of setup, the Airflow workers are running on the same machine as the scheduler, meaning we only need to set up 2 compute resources for Airflow, one for the web server and one for the scheduler. Figure 15.1. Both the web server and scheduler components will need access to a shared database, the Airflow Metastore, and, depending on the version and configuration of Airflow, shared storage for DAGs and logs. Depending on how you manage your data, you'll also want to have some external storage set up for storing any input and output datasets. Footnote 1. In Airflow 1, both the Airflow web server and scheduler require access to the DAG storage by default. In Airflow 1.10.10, an option was added for the web server to store DAGs in the Metastore, so that it no longer requires access to the DAG storage if this option is enabled. In Airflow 2, this option is always enabled, so the web server never needs access to the DAG storage. Besides these compute and storage resources, we also need to consider networking. Here we have two main concerns: how we will connect the different services together, and how we organize our network setup to protect our internal services. As we will see, this typically involves setting up different network segments, public and private subnets, and connecting the different services to the appropriate subnets. Figure 15.2. Additionally, a complete setup should also include services that protect any publicly exposed services from unauthorized access. This gives us a fairly complete overview of the required components for a deployment based on the local executor. Moving to the Celery executor, which provides better scaling by running workers on separate machines, requires a little bit more effort, as Celery-based deployments require two extra resources: a pool of extra compute resources for the Airflow workers and a message broker that relays messages to the workers. Figure 15.3. These architecture sketches should hopefully give you some idea of the resources needed to implement the Airflow deployments in a cloud setting. In the following chapters, we'll dive into implementing these architectures on the different clouds. Section 15.2. Cloud-specific operators and hooks. Over the years, contributors to Airflow have developed a large number of operators and hooks that allow you to execute tasks involving different cloud services. For example, the S3 hook allows you to interact with the AWS S3 storage service, for example, for uploading, downloading files, while the BigQuery execute query operator allows you to execute queries on Google's BigQuery service. In Airflow 2, these cloud-specific hooks and operators can be used by installing the corresponding provider packages. In earlier versions of Airflow, you can use the same functionality by installing the equivalent backport packages from PyPI. Section 15.3. Managed Services. Although rolling your own Airflow deployment can give you ultimate flexibility in how you use it, setting up and maintaining such a deployment can be a lot of work. One way to avoid this burden is to use a vendor-managed service, where you can offload most of the work to an external provider. This provider will then typically give you tools for easily creating and managing new Airflow deployments without all the hassle of rolling your own. Usually, the provider also promises to maintain the underlying infrastructure so that you don't have to worry about keeping your operating system and/or Airflow installation up to date with the latest security patches, monitoring the systems, and so on. Three prominent managed Airflow services are Astronomer.io, Google Cloud Composer, and Amazon MWAA. In the following sections, we'll provide a brief overview of these services and their key features. Section 15.3.1. Astronomer.io. Astronomer.io is a Kubernetes-based solution for Airflow that can be used as a SaaS, software as a service, solution, Astronomer Cloud, or can be deployed to your own Kubernetes cluster, Astronomer Enterprise. Compared to vanilla Airflow, Astronomer also provides extra tooling that helps you easily deploy Airflow instances from the UI or from their custom-built CLI. The CLI also allows you to run local instances of Airflow for development, which can ease DAG development, assuming you have Kubernetes available on your development machine. Because it is built on Kubernetes, Astronomer.io should integrate well with any Kubernetes Docker-based workflows you may be used to. This makes it easy to, for example, run your tasks in containers using the Kubernetes executor and Kubernetes pod operator. Other deployment modes using the local executor or Celery executor are also supported, giving you a lot of flexibility in how you run your jobs. Astronomer also allows you to customize your Airflow deployments by specifying extra OS or Python dependencies that should be installed into the cluster. Alternatively, you can build a custom Airflow base image should you need that extra flexibility. Pricing for the SaaS solution is calculated using astronomer units, AUs, with different configurations costing a different number of AUs. For an overview of these costs, see the Astronomer website, here. It's also worth mentioning that Astronomer.io employs several key contributors to the Airflow project. As such, they contribute strongly to the Airflow project and regularly drive the development of important improvements to the open-source version of Airflow, making sure everyone can benefit from these new features. Their Helm charts for deploying Airflow on Kubernetes are also freely available online, should you want to try them outside of the Astronomer platform. Section 15.3.2 Google Cloud Composer. Google Cloud Composer is a managed version of Airflow that runs on top of the Google Cloud Platform, GCP. As such, Cloud Composer provides an easy, almost one-click solution for deploying Airflow into GCP that integrates well with its different services. GCP will also take care of managing the underlying resources, but you only pay for the resources they use. You can interact with Cloud Composer using the GCP CLI and/or monitor the state of your cluster or clusters from within the GCP web interface. Similar to Astronomer.io solution, Cloud Composer is also based on Kubernetes and runs on the Google Kubernetes Engine, GKE. A nice feature of Cloud Composer is that it integrates well with different services within GCP, such as Google Cloud Storage, BigQuery, etc., making it easy to access these different services from within your DAGs. Cloud Composer also provides a lot of flexibility, WRT, how you configure your Kubernetes cluster in terms of resources, and so on, so you can tune the deployment to your specific needs. Similar to Astronomer.io, you can install Python dependencies into your Airflow cluster or clusters using the web interface or the GCP CLI. Google Cloud Composer includes a fee for the environment itself, number of nodes, database storage, network egress, etc., in addition to costs for underlying services, GKE, Google Cloud Storage, etc. For an up-to-date overview of these costs, see the GCP website here. Footnote 2, used by Cloud Composer for storing DAGs and logs. As a strong proponent of open-source software, Google also regularly contributes to the Airflow open-source project and has helped develop an extensive suite of operators for its different services to enable their usage from within Airflow. Footnote 3. Note that you don't necessarily need to use Google Composer to use these operators, as they also function perfectly fine from within Airflow, assuming permissions are set up correctly. Section 15.3.3 Amazon Managed Workflows for Apache Airflow. Amazon Managed Workflows for Apache Airflow, MWAA, is an AWS service that allows you to easily create managed Airflow deployments in the AWS cloud, similar to Google's Cloud Composer. When using MWAA to run Airflow, the service will manage the underlying infrastructure and scale your deployment to meet the demands of your workflows. Additionally, Airflow deployments in MWAA are also promised to integrate well with AWS services, such as S3, Redshift, SageMaker, and with AWS CloudWatch for logging, alerting, and AWS IAM for providing a single login for the web interface and securing access to your data. Similar to the other managed solutions, MWAA uses the Celery executor for scaling workers based on the current workload, with the underlying infrastructure managed for you. DAGs can be added or edited by uploading them to a predefined S3 bucket, where they will be deployed into your Airflow environment. Similar S3-based approaches can be used to install additional Airflow plugins or Python requirements into the cluster as needed. Pricing includes a base fee for the Airflow environment itself and an additional fee for each of the Airflow worker instances. In both cases, you have the option to choose between small, medium, large machines to tailor the deployment to your specific use case. The dynamic scaling of workers means that worker use should be relatively cost-effective. There is also an extra monthly storage cost for the Airflow Metastore, as well as any storage required for your DAGs or data. See the AWS website for an up-to-date overview and more details. Here. Section 15.4. Choosing a deployment strategy. When picking a platform for running your Airflow workloads, we recommend examining the detailed features of the different offerings and their pricing to determine which service is best suited for your situation. In general, rolling your own deployment in one of the clouds will give you the most flexibility in choosing which components to use for running Airflow and how to integrate these into any existing cloud or on-site solution you already have. On the other hand, implementing your own cloud deployment requires some considerable work and expertise, especially if you want to keep a close eye on important factors such as security and cost management. Using a managed solution allows you to push many of these responsibilities to a vendor, allowing you to focus on actually building your Airflow DAGs rather than on building and maintaining the required infrastructure. However, managed solutions may not always be flexible enough for your needs if you have complicated requirements. As an example, some important considerations may include the following. Do you want to use a Kubernetes-based workflow? If so, Astronomer.io or Google Cloud Platform provide an easy approach. Alternatively, you can roll your own Kubernetes cluster, for example, using the Helm chart from Astronomer.io. Which services do you want to connect to from your DAGs? If you're heavily invested in GCP technologies, using Google Cloud Composer might be a no-brainer due to the easy integration between Composer and other GCP services. However, if you're looking to connect to on-site services, or those in other clouds, running Airflow in GCP may make less sense. How do you want to deploy your DAGs? Both Astronomer.io and Google Cloud Composer provide an easy way to deploy DAGs using the CLI, Astronomer.io, or a cloud bucket, Cloud Composer. However, you might want to consider how you wish to tie this functionality into your CI/CD pipelines for automated deployments of new DAG versions and so on. How much do you want to spend on your Airflow deployment? Kubernetes-based deployments can be expensive due to the costs of the underlying cluster. Other deployment strategies, using other compute solutions in the cloud, or SaaS solutions like Astronomer.io, can be cheaper options. If you already have a Kubernetes cluster, you may also want to consider running Airflow on your own Kubernetes infrastructure. Do you need more fine-grained control or flexibility than provided by the managed services? In this case, you may want to roll your own deployment strategy, at the cost of more effort in setting up and maintaining the deployment, of course. As this short list already demonstrates, there are many factors to consider when choosing a solution for deploying your Airflow cluster. While we cannot make this decision for you, we hope this provides you with some pointers to consider when choosing a solution. Summary. Airflow consists of several components, for example, web server, scheduler, Metastore, storage, that need to be implemented using cloud services for cloud deployments. Airflow deployments with different executors, for example, local, Celery executors, require different components that need to be accounted for in the deployment strategy. For integrating with cloud-specific services, Airflow provides cloud-specific hooks and operators that allow you to interact with the corresponding service. Vendor-managed services, for example, Astronomer.io, Google Cloud Composer, Amazon MWAA, provide an easy alternative to rolling out your own deployment by managing many details for you. Choosing between vendor-managed services or creating your own cloud deployment will depend on many factors, with managed solutions providing greater ease in deployment and management at the expense of less flexibility and possibly higher running costs. Chapter 16. Airflow on AWS. This chapter covers designing a deployment strategy for AWS using ECS, S3, EFS, and RDS services. An overview of several AWS-specific hooks and operators. Demonstrating how to use AWS-specific hooks and operators with a use case. After our brief introduction in the previous chapter, this chapter will dive further into how to deploy and integrate Airflow with cloud services in Amazon AWS. First, we'll start by designing an Airflow deployment by mapping the different components of Airflow to AWS services. Then we'll explore some of the hooks and operators that Airflow provides for integrating with several key AWS services. Finally, we'll show how to use these AWS-specific operators and hooks to implement a use case for generating movie recommendations. Section 16.1. Deploying Airflow in AWS. In the previous chapter, we described the different components that comprise an Airflow deployment. In this section, we'll design a few deployment patterns for AWS by mapping them to specific AWS cloud services. This should give you a good idea of the process involved in designing an Airflow deployment for AWS and provide a good starting point for implementing one. Section 16.1.1. Picking cloud services. Starting with the Airflow web server and scheduler components, one of the easiest approaches for running these components is probably Fargate, AWS's serverless compute engine for containers. One of the main advantages of Fargate, compared to other AWS services like ECS or EKS, is that it allows us to easily run containers in AWS without having to worry about provisioning and managing the underlying compute resources. This means we can simply provide Fargate with a definition of our web server and scheduler container tasks, and Fargate will take care of deploying, running, and monitoring the tasks for us. Footnote 1. Elastic Compute Service, similar to Fargate but requires you to manage the underlying machines yourself. Footnote 2. Elastic Kubernetes Service, AWS's managed solution for deploying and running Kubernetes. For the Airflow Metastore, we recommend looking toward AWS's hosted RDS solutions, for example, Amazon RDS, which helps with setting up relational databases in the cloud by taking care of time-consuming administration tasks, such as hardware provisioning, database setup, patching, and backups. Amazon RDS provides several types of RDS engines you can choose from, including MySQL, Postgres, and Aurora, which is Amazon's proprietary database engine. In general, Airflow supports using all of these backends for its Metastore, so your choice may depend on other requirements, such as cost or features such as high availability. Footnote 3. Amazon RDS includes several database types, such as PostgreSQL, MySQL, and Aurora. AWS provides several options for shared storage. The most prominent is S3, a scalable object storage system. S3 is generally great for storing large amounts of data with high durability and availability for a relatively low cost. As such, it is ideal for storing large datasets, which we may be processing in our DAGs, or storing temporary files, such as the Airflow worker logs, which Airflow can write to S3 natively. A drawback of S3 is that it cannot be mounted as a local file system into the web server or scheduler machines, making it less ideal for storing files such as DAGs, which Airflow requires local access to. In contrast, AWS's EFS storage system is compatible with NFS and can therefore be mounted directly into Airflow containers, making it suitable for storing DAGs. EFS is, however, quite a bit more expensive than S3, making it less ideal for storing data or our log files.